be 5. This is an approximation model that we would like to start from. And we would like a quantity or a metric to say how well we are doing on our data. So, and then the error or the loss or the cost is one of the pillars. And we need an estimation algorithm like gradient descent in order to make this approximation model fit our data well in order to decrease the error. I'm going to go through each one quickly and then stop and explore the estimation algorithm more لأنه هي خاصة ب our lecture today. Data can vary from many different domains. You can think of data in supervised learning sense as tuples. I have the example and the label. يعني the example and the correct answer. The correct answer may be the exploitation energy of a chemical bond, or it may be a 1-0, sad, bad, happy, مش عارف شو. It may be a class, a discrete, or a number that belongs to R. And we need to think as the data is, the features are coming from a certain distribution over X, and the labels are coming from a hidden function, from the physical world regularization. There is a function somewhere that's relating this X to this Y, and the whole headache of machine learning is to approximate this function, to make a function F that we're going to approximate F star, which is the function that is regulating this world. The model or the hypothesis, it's a function that we try to estimate the F star function within. It may vary from a linear regression to a neural network مثل ما حكينا بس امبارح, and in between فيك تختار polynomial functions, and going beyond neural networks we can detach a neural network with an RL detachment in order to make any function we want, or we can combine both. Many experts, a linear regression plus a neural network that will gonna help each other get the answer of F star. So basically, the model is a function. It's mapping X to Y hat. Since we don't know the Y, it's to Y hat. And a very important phenomenon when we need to look at the functions at hand or the models is to pay attention to something called the capacity of this model or the complexity of this model. A capacity for a model in the sense of neural networks, it may be simply the number of neurons, or it may be for certain applications like deploying on edge or very sensitive applications, it may be the number of bits it will take us to place this model on a certain chip. In case of any function, we can make use of certain metrics or certain quantities to say more about the complexity of this function. Like we can make use of something called the Sobolev norm, in which it will gonna say about the second order derivatives. So basically, if this quantity is small, it means that the derivatives are small, and then it's a smooth function. If this function is very big, if this quantity is very big, then the function is not smooth and the derivatives are very high. But this is a detail. Just look at the complexity as how much capacity or how much strength my model have. And to see the capacity of models more, I'm showing here data points اللي هن بالX, the red X, the hidden function F star, which is in blue, and I'm trying to fit two models. The first is a neural network with 5 neurons, and the second is a polynomial of degree 14. Clearly, you can see that the neural networks, a neural network with 5 neurons, will gonna fit my data better than a polynomial of degree 14. And this is gonna show you the capacity of models. We're gonna say that the neural network with 5 neurons have more capacity to fit the data more than the polynomial of degree 14. Okay, anything not clear لهلا؟ إذا في شيء
أنا عندي سؤال.
Yes.
ما كتير فهمت شو يعني capacity. شو الفرق بينه وبين accuracy؟
Okay, so I'm trying to introduce terms one by one. هلا ما حكيت عن accuracy شيء. So clearly capacity is different than accuracy. Capacity is the strength of our model. It may be the number of neurons. So I'm going to say that a neural network of 10 neurons is stronger أو عندها capacity أكتر from a neural network that have 5 neurons. سكر المايك please. And I'm going to say that a neural network of 10 neurons have more capacity than a neural network of 5 neurons. Capacity is strength. يعني the ability of a model to fit certain data is called capacity. We can think of it as complexity. Complexity of a model يعني function عندي أقوى. A linear function is the most is the simplest model ever. The next simplest is يعني الأقوى منها بشوي is the piecewise linear, and then we can go for polynomials then in neural networks.
يعني فينا يعني نعملها كوانتايزيشن بالنمبر اوف بارامترز بكل بساطه.
مش quantization quantifying قصدك انت. quantization يعني compressing.
ايه انه كل ما كان عندي بارامترز اكتر كل ما كانت الكاباسيتي اكتر كل ما كانت كومبلكسيتي اكتر.
Right. And for any function بهالعالم فينا to measure this quantity. مثلا حكيت عن السبل of norm and فيك تاخذ any norm بدك اياه بالعالم. فيك انت تحسب the second derivatives وتجمعهم and you're gonna say that this is a metric. هلا جماعة
مش مرة
بقوموا لينا إذا قلنا metric have a certain definition بالماث. بس إنه quantity أنا قصدي.
بس أنت قلت شغلة إنه a model with a higher capacity is able to fit the F star إنه يقدر يلاقي ال F star أحسن.
Yes.
بس ما ضروري.
Right.
ضروري؟
إنه it will gonna overfit eventually بس إنه عندها more capacity. صح؟
إيه.
Yes. Think of it as GPT and any neural network. هلا إذا you pass هلا certain tasks بالGPT بدهم one shot. So with one shot with one shot with one prompt you can take the answer. بينما بالneural network it may need some fine tuning أو some regularization. The error is the third pillar, and in machine learning we try to decrease a certain quantity. We call it an error, and more specifically, I'm just introducing some terminologies, some fancy terminologies, since they appear in papers and in literature بشكل عام. We try to decrease something called the empirical loss, which is not the true loss. Since we don't have the full data, so we can't test our model على كل الداتا بالعالم, على كل data distribution. So we're gonna test it on the data we have, which is called the test data بالعادة, or the trained data. You can think as the data distribution that we have in my database when I am training my model. We test our model عليها, and this is called the empirical loss, and we try to decrease this loss at every time. Loss cost, I'm intervening those terms, بس فيك تفكر as the loss is the point-wise difference between the label and the approximation of my model, and the cost is the average of all the data points. Any question لهلا? Since we're gonna عم نقرب شوي على our session. Okay, and هلا لما صار معي data and I have a certain metric to analyze on, I need to choose a model, and I have a big space or a big pool of models to choose from. But as a computer scientist or as an engineer, I need to pick something deterministic. So I'm gonna say that out of the space of all neural networks, I need certain complexity to start from. So I choose my model before training. I choose the capacity of my model before training, and I say that I'm gonna train on neural networks with 5 neurons or with n neurons. So we need also to choose a good point to start from when we are training our models, and we need to be very careful when choosing this point. So if we choose a very big model, we're gonna overfit, and a very small model we're gonna underfit, and it depends on the optimization algorithm. But the basic idea is that any assumption we do in machine learning, we need to pay for it. Any assumption we do. The first assumption we did is that we don't have the full data in the world. So we are training on a very limited data set. This is called the statistical error. We have an error by nature اللي هو we need to pay for not having the full data. We have a second error which is called the approximation error. The second assumption I did is that I'm gonna train on a neural networks, more specifically on a neural networks with n neurons. Who said that this kind of neural networks will gonna fit my data well? So this is an approximation error. And then there is an error in which is called the optimization error. And this optimization error will gonna pay for or penalize me choosing certain algorithm and running this algorithm to fit the data well. And we're gonna see, due to the stochasticity of the problem and due to the complexity of the problem, I'm not gonna find a global optima or a perfect answer at each time. So this is an optimization error that it's due to the optimization algorithm, اللي هي gradient descent in the most case. And today we are trying to decrease or find out ways to decrease the optimization error. So the statistical error, we can do some tricks لحتى نخففه. They are related to geometry and data augmentation. The approximation error, we can do some tricks لحتى to decrease it. But the scope of today's session is to decrease the optimization error, in which we can decrease it by finding better algorithms to train our models, to find better gradients, to find better iterative algorithms to train our model upon. هلا حرقتها قلت gradients, but we're gonna build upon to reach gradients. طيب today's lecture
هلا
we're
بس
gonna
شو
start
علاقة
from
الاوبتمايزيشن ايرور بالكوست اللي كنت عم تحكي عنه قبل شوي؟
yes. So those three errors, هلا هيدي نحن بعتقد مرة عملناها as internal session, بس those three errors, sorry, are implicitly within the cost function. Within the cost function, you pay for the point-wise difference between the label and the approximation, the approximated answer. But implicitly, you're paying three things. The first is your model is not doing well because of three things. Because of the statistical error, you don't have the full data. Because you chose the wrong model. This is the approximation error, and an optimization error, which will gonna there's no guarantee انه you will find a perfect solution.
سؤال
And those are implicitly within the cost function, within this point-wise difference.
سؤال
Yes.
هلا الستاتستيكال ايرور واضح ما فينا نخلص منها باي شكل من الاشكال، لان ما في شيء عندنا ما فينا نخلص، عم قول يعني فينا نحسنها. بس
Okay.
الاوبتمايزيشن ايرور ما فينا نخلص منها، انه الفانكشن اللي عندي اياها اوصل للمينيموم فيها.
Yes, 100%. Like in linear regression. Most probably we're gonna get a zero optimization error. Why? Because it's a convex optimization problem, and you can solve it in a closed form and then get the perfect weights. صح? But we're talking about deep learning. In deep learning, due to the stochasticity of the problem, we have many things that are random. مثل هلا يمكن هو قصص لازم احكيهم بعدين، بس مثل the batch size, the batch size. شو في بعض قصص random, which was the weight initializations. Due to the stochasticity of the problem, by any chance مش حيكون عندي a deterministic way to find the perfect weights. Good. جاوبتك على سؤالك؟
السؤال شو يعني stochasticity؟
قلت لك randomness. قلت due to the randomness of the problem. Random over time is بدك. يعني the batch size I'm choosing it random at every iteration مثلا. خلاص فكر فيها randomness هلا. Okay. طيب. Today's lecture we're gonna take a closer look at the optimization error and how we can minimize this optimization error. لحسن ترمس ماخذ 100 على 338 بس I'm gonna introduce a term which is called NP-hard problems. ما راح احكي عنه شو هو، بس think of it as a very complex computer science problem that we hope to solve someday. But finding a global optima or finding a perfect solution in deep learning, يعني finding the weights that are going to give us a perfect solution or perfect error is called an NP-hard problem. For now, think of it as a very complex problem. And in this lecture, we're going to try to loop around and find the stuff around the minimals in order to overcome this curse in optimization. يعني today we're going to scoping in the optimization ما خصنا لا بالstatistical ولا بالapproximation. As you can see, this is what we think of as deep learning functions, خصوصي deep learning cost functions. But thing is, and we do an assumption, إنه ML models are not very harsh. They are benign landscapes مثل الصورة الحلوة اللي شايفينها هون. There are some landscapes and the gradient descent will gonna work well and we're gonna converge to some optima, to some perfect solution. هلا بنحكي why we're not gonna take a perfect solution, but we're gonna find something called the local minima, which is a partially perfect solution. And it turned out that it works well. هلا طلعنا من فكرة ال NP hard problems. A gradient descent, we're gonna find our solution in polynomial time. Polynomial is good, exponential is bad in computer science, so we stick with polynomial. With this guarantee that this will work, we can explain and discuss together how we're gonna make this happen. But for now, I need you to convince yourselves, and yes, search in this space it's an NP hard problem, but with ways around, we can find a partially perfect solution with a polynomial time. And now we can see how. في حدا عنده شي سؤال على السيت اب؟ Okay. Let's consider a small gate in which it's a small function. It's x times y, and assume x is 2 and y is 5. Who can give me a systematic way to every time increase the output of this gate? Like at the first iteration, it's 2 times 5, it's 10. Give me a systematic way to increase the output in a systematic way, and you can assume that x and y are not positives or negatives at each time, and you need to modify them to increase the output. يلا.
كيف يعني نحل له اوبريشن انه امس فين نعمل
لا مش
لكل واحد نرجع نسمعه
لا مش حيلا اوبريشن. I need a systematic way to modify x and y, and أنا in neural networks or in machine learning, I can modify the weights to change the cost. هلا بدي a systematic way to change x and y in order to decrease the loss, to increase the output. هلا بعد ما في عندنا the notion of loss.
نعمل derivative.
بلا اوكي, this is a good way. It turned out انك انت مسبق علينا.
I decrease the maximum بيناتهم.
I need the most trivial one. The most trivial. I decrease the maximum بيناتهم.
ايه.
decrease انا بدي اعمل
انت قلت لنا بدك تعمل له minimize، بدك تعمل له maximize.
لا بدي اعمل له maximize. سوري.
ايه I increase the minimum بيناتهم.
You increase the minimum بيناتهم. وليش مش الماكسيموم؟
لأن حساب الثاني نيجاتيف.
ما بتعرف. I need to check at every time يعني؟
لا أنا ما أصلا ما اقترحت هيدي السولوشن، لأن في حال كان في وحدة نيجاتيف وحدة بوزيتيف تخرب الدنيا.
اوكي then.
فاقترحت شيء دائما حيعمل لها انكريز، هو انه بكبر الاصغر.
اوكي how much you are limited هلا انت هون لما تكبر الاصغر؟
شو قصدك limited؟ بشو؟
يعني في مرة يعني تكبره by how much؟
بعدين بحكي كان -2 -3، يعني ممكن إذا زدنا واحدة يصغر التوتال فاليو، التوتال برودكت قصدي.
Right. It turned out that the most trivial thing to do is to change x and y randomly. هلا قد ما فكرت ب ways to do them, you're gonna reach bottlenecks at every time. ممكن يصيروا اثنيناتهم نيجاتيف، يقلبوا النيجاتيفز، مرات بس تعمل ابديت لواحد ما عادش يعمل ثاني ابديت. There is many corners بقلب هيدا السوليوشن. Turned out that if you need to maximize x times y, try to add random quantities على x and y, and at each time you keep track with the maximum and تطلع هيدي. For some problems it works. For some problems that are small, it works like x times y. But for neural networks, we can't do this. We can, as computer scientists and engineers, we can't rely on random algorithms, on randomized algorithms. So we need a more systematic approach to do it. مين قال gradients قبل شوي؟
أنا قلت derivatives.
Yes. مين قال derivatives؟ أنت يا علي؟ Okay. So derivative of a function with respect to some variable, we're gonna tell you this fact. If you compute the derivative of a function with respect to a variable, we're gonna tell you that if you move this variable in the direction of the derivative, you're gonna maximize this function. As simple as this. The mathematical definition of a derivative is f of x, assuming f is your function and x is your variable, is your input, f of x plus a minus f of x over a, where a is epsilon. This is the derivative. How the function responds to small changes in the input. Basically, what we are doing is differentiate the function with respect to the variable, and you're going to get the direction of the steepest increase. So basically now I have a systematic approach in order to say I'm going to nudge my parameters in this direction, and I'm guaranteed by the mathematics regulations, I guarantee by mathematics that I'm going to increase my function. So calculus gave us a way in order to see the direction of the steepest increase, which is the gradients. So I'm going to make use of it. And if I need to maximize my function, I'm going to nudge my parameters in the direction of this gradient. What's the intuition? The intuition is that in neural networks we have many parameters, those W's. We have non-linearities. We have operations like sum. And the problem is that I need to calculate the effect of all of these operations on the loss, which is I need to minimize for the effect of these all operations on the loss, and then I need to tweak those parameters in order to decrease my loss. In other words, we need the gradients for every operation and for every weight. And in order to do this, we should calculate the effect of every weight and every operation on the loss, and then nudge the weights. I need to minimize nudge the weights in the opposite direction of the gradients. Things will gonna become clear in a second, but this is the basic approach. This is the basis approach. We're gonna compute some derivatives for every weight and calculating the operations also. And then when each weight have its own gradient, we're gonna nudge it in the opposite direction. Yeah, put a minus in the direction of the gradient, in the opposite direction of the gradient. هلا gradients gave us the direction. من بيقول لي who will give us the magnitude of this nudge?
The learning rate?
100%. So the learning rate will gonna give us the magnitude, and the gradient will gonna give us the direction plus minus, and we're gonna multiply to the learning rate, and then put another minus since we need the opposite direction. Is it clear? Okay. To make it more robust, think of it as إنه اللي حكاه باسل is the figure على left, to your left, is the feed forward. We're gonna input X to a neural network, and then we're gonna have some cost, some loss. Let's zoom in to a neuron and say that this S is an input that is going into a nonlinearity of a function and is producing Z. Or you can think of it as ZA, as أنت مخ terminology صغير. In the basic sense, it's an input going to a nonlinearity, and I'm having an output. And let's zoom in here and see what's happening. In order to see or to measure how this input is influencing the cost, I need to compute certain terms around S. مثل I need how everything from Z وطلوع influences this cost, and I'm gonna assume this is a gradient that is given to me, and it's the gradient of the derivative of the cost with respect to Z. So I know how Z influences the cost, and then I need to multiply it with a gradient which is moving this S inside the nonlinearity. So I need H prime S, and I'm gonna multiply those, and then I'm gonna have the effect of S on the cost. الخلاصة يعني إنه to find how S influences the cost, I need to see how Z influences the cost and how passing it to this nonlinearity influences the cost. Multiply those. This is a combined influence, and it's the gradient of S. And we're gonna see a systematic way to do this. And هلا بقول نشوف بس إنه في حدا عنده سؤال هلا. ما حدا؟ Okay. The problem is harshly big لأنه you can think هلا هيدي is a truncated picture كمان, but this is a computer vision model called AlexNet where it have millions of parameters. So we need a very scalable way and a very efficient way to compute those gradients. Yes, لأنه I can't simply nudge the parameters up and down شو اسمه and minus them and subtract them, and then I can get the gradients. I need a very scalable way and very efficient way, which is backpropagation. Backpropagation is an algorithm in which it will analytically, يعني with the use of calculus, specifically chain rule, we're gonna get us the gradients of every parameter. Instead of using the numerical gradient, which is nudging all the parameters up, then down, then scaling this with epsilon. So backpropagation is a very old algorithm. بأي سنة يا باسل؟
1986.
It's in 18 okay بال
1986
بال 1986 يعني كثير قديمة. عملها واحد اسمه جيف هينتون وير عملها بوقت ما كان حدا سامع بالديب ليرنينج يعني ما كان حدا سامع بالديب ليرنينج where we have now it's the backbone algorithm behind deep learning models. Any question على setup? We're going to go through the examples right now. Okay. So now I'm gonna give you two examples on a walkthrough on how backpropagation works. The exact thing applies to how PyTorch manages the gradients. So we're gonna go through these examples, and these examples are exactly how PyTorch deal with the gradients. They are in the shape of graphs, and these graphs are called auto-differentiation graphs. And whenever you do in PyTorch grad equal true, you're managing to store this graph somewhere in your memory. So we're gonna do backpropagation on a very simple example in which it's the function x plus y all times z. So in the differentiation graph, we have x plus y in a gate, and it's producing a local variable called the q, and then I'm multiplying the q with f, and I'm getting my answer. And I need now, given that the input is -2, 5, -4, I need to distribute gradients for every input x, y, and z. We're gonna do what Basil علمنا امبارح, which is the forward propagation. We're gonna pass our inputs into the graph. X plus y is equal to 3, and all times z it's equal to -12. Good لهون. هيدا the forward pass. Now the backward pass, we're gonna get me the f, which is, as I'm assuming here that it's the last gate, the f by the x, and the f by the y, and the f by the z. via backpropagation. And I need to start. Okay, the definition of backpropagation is exactly this: recursively applying chain rule over the layers of a neural network. So it's recursive and it's chain rule. For recursion, we need a base case, and it is the influence of f on f, which is 1, right?
سؤال بس
اللي
قبل هون، يعني اذا فينا نرجع لقبل ما بلشوا يبينوا بالاحمر، ايه نحن هيدي الفورورد باس صح ولا لا؟
لحد هون يس فورورد باس.
اوكي، بس بدنا نعمل الباك بروباجيشن نعملها يعني بنعملها اوكي لا انا لخبط. اوكي هلا after the forward pass لازم نشوف الكوست صح؟
رايت. هلا I'm assuming here انه الكوست اللي هو اللاست جيت بنيورال نتورك is -12. خلص هو اللاست جيت بهذه السيركت تبعي. This is a circuit that we are trying to backpropagate. فينا نطلع من فكره انه هي هلا نيورال نتورك، لانه هلا بعدين we link it. Okay. So since it's recursive, I need a base case which is 1, right? The influence of f with respect to f is 1. And now I need to distribute gradients over q and z لانه هن اللاير اللي دغري وراي. It's recursively applying. I apply it to f علق ل q and z. هلا f represents q times z, and if I need to derive f يعني df by dq it's z, df by dz is q. So a very important analogy here is that multiplication gates swap the gradients, swap the input with the gradients. So now the gradient of z is q, the gradient of q is z. So I can distribute directly the gradient of z, which is q3, and the gradient of q, which is z -4. في حدا عنده أي سؤال هلا؟ هيدي الستep فهمينها منيح؟
هلا هون بس لانه مالتيبليكيشن هيك طلعت صح؟
يس لانه يس لانه مالتيبليكيشن it will swap the input. هلا بنشوف الاديشن شو حتعمل.
اوكي.
And now I need to get df by dy and df by dx. df by dy as the q, I'm gonna look at the direct output اللي هو q. q is x plus y. This q right here. But ما بدي انسى, and here where things get interesting, انه q itself influences f. So y will gonna influence q, and the q will gonna influence f. So if I need to calculate the effect of y on f, I need to calculate also the effect of q on f. And if I need to quantify this, I need also to multiply or to scale with the effect of q on f. So the real gradient of y is the q by dy, its effect on q, and the f by the q, its effect on f. Is the chain rule مفهوم منيح and understandable? If this is clear, now with this rule, I can simply distribute the gradients in the same way اللي عملته للZ والQ. So the derivative of x plus y with respect to x is 1, and of x plus y with respect to y is 1. So I distribute the gradient of the q by dy. هلا عرفتوا هذا صار 1, and now I need to chain it. I need to chain it with the gradient تبع ال q, which is the f by the q. So it's now -4. Important terminology. I'm gonna call the f by dy the downstream gradient, the gradient that I'm working on. I'm gonna call the q by dy the local gradient, which is the effect directly on the gate. I'm gonna call the f by the q a gradient that it's coming to me from the other layers or the other gates, the upstream gradient. Same thing applies to to x, sorry. So the q by the x is 1, and the f by the q is -4. So also I'm gonna distribute the gradient directly, وكمان بتطلع -4. Is this clear?
سؤال، ليش استخدمنا تشين رول؟
Yes. طيب نرجع لهون. I'm gonna push X into the neural network بهذه الصورة اللي هون. And then I'm gonna zoom in into a certain neuron. In this neuron, I have some input S. It's going into a nonlinearity. It's producing Z. This Z is propagating also in the network to get some cost. I need to calculate the effect of S on this cost. So I need to calculate things around it. Like I need to calculate the effect of Z on C, since Z is produced by S. I need also to calculate the effect of using this nonlinearity on C. I multiply those مع بعض أو I scale those مع بعض, and this is the total effect of S on C. يعني to get the gradient عندنا two ways, numerical أو analytical. Numerical, we use the definition. We nudge every parameter up and then subtract this from the original output of the function, scale it by epsilon. And this is عندها مشكلة يعني هلا بنحكي عنه إذا بدكم بالآخر. And or use backpropagation, in which we recursively apply chain rule على كل layer, and then I can produce the total effect of every parameter on the cost. مفهومة؟ مفهوم يا علي؟ اوكي. Now let's zoom in, نطلع من قصة الجيتس and zoom in into a neuron. In a neuron, I'm gonna get two inputs basically. لا مش two inputs. I'm gonna make an operation between two operands, the input and the weights, and I'm gonna get some answer. Every neuron will gonna have some gradient in front of it. We call it the upstream gradient. It's the dl by dz, or the effect of its output on the cost. Each operand من هول two operands اللي عم يشتغلوا عندي in a neuron الweights والinputs will gonna have its local effect on z. So dz by the x and dz by the y. I need to chain those مع بعض, the local gradient and the upstream gradient, to produce the downstream gradient, which is the effect of x itself on the cost and effect of y itself on the cost. And this is true for every neuron. So I take this downstream gradient, and it's now an upstream gradient, and I propagate it back to all the layers behind me. And this is the recursion stuff. Is this good? منيح الانالوجي تبع النيورون؟
بس فيك ترجع توضح شو هي الاكس والواي؟
Yes. A neuron will gonna do certain operation between two things, the weights and the input. At a very basic sense, it was gonna do wx plus b with a certain nonlinearity, right?
تمام.
Okay. Every neuron will gonna have an output, and this output have its effect على loss. If I happen to know this effect اللي هو dl by dz, يعني the effect of the output on the loss, I need two things لحتى اجيب لي gradients تبع الانبوتس وتبع الويتس. I need the local effect اللي هو the effect of the inputs على الاوتبوت and the effect of the weights على الاوتبوتس. So this is called the local gradient. You can think of them as dz by dx and dz by dw. And then I need to combine this or scale it with the upstream gradient اللي هو the effect of the output على loss. And when I scale those, عندي the total effect of the weights على loss and the input على loss. And then I need to propagate this لكل النيورونز اللي قبلي على layer اللي قبلي يعني. If it happened انه انا in a certain layer.
اوكي تمام.
We're gonna go through another example, but we're gonna introduce also the first optimization in backpropagation algorithms in PyTorch. مين بيقول لي هذه الفانكشن شو هي؟ Taking x and w in this way and doing 1 over 1 plus e to the minus the linear sum, the linear multiplication fee. The weighted sum, sorry.
في فواز هو يقول شو هي هاي؟
عندك ما خصني أنا.
فواز شو هيدي؟ function.
هيدي مش سيجمويد.
Son, هذه السيجمويد function, and this is the sigmoid function that we're gonna take any number on R and squash it. And squash it between 0 and 1. If I need to make the graph of the sigmoid, I'm gonna input every parameter and every input into gates pluses and minuses to make the weighted sum, and then I need to inverse this. بيصير معي هيدا الquantity minus this thing, and then I need to put it into an exponent, add a 1, and then flip it, أعملها 1 over x. And this is gonna get me the sigmoid activation of this weighted sum. I just dropped random numbers here to make the forward pass. The base case, as always, it's 1. It's the effect of the last gate on the last gate, so it's 1. And now I need to compute the first iteration in the backpropagation algorithm. I'm having 1.37 passing into a function which is 1 over x and producing some output. The upstream gradient, or the effect of this output on the loss, is 1. The downstream gradient is the local gradient, so I should see how this 1.37 behaves within this 1 over x. The derivative of 1 over x I can store it somewhere in my program. It's minus 1 over x over x squared. Since it's x to the power minus 1, ننزل minus 1, we do minus 1 again, تطلع معك minus 1 over x squared. So the local gradient is minus 1 over x squared, يعني هي minus 1 over 1.37 squared. This is the local gradient. To get the upstream gradient, I'm gonna multiply this local gradient with the downstream one, and then I got the full gradient, the full effect of this number 1.37 on the loss. I need to do this for every function gate and also distribute it over the pluses and minuses over the weighted sum in order to reach having the gradient for every parameter and input. But a good way to fold the number of gates to decrease the number of gates, since the number of gates is compute and memory. It's always good to fold the number of gates or decrease the number of gates. I can realize that this is the sigmoid activation, and I can replace this with one gate called the sigmoid activation. If I differentiate, if I take the sigmoid activation, which is 1 over 1 plus e to the minus z or x, and I compute its derivative manually, I'm gonna square the denominator, and then I'm gonna do uv prime plus v prime u, and I can split it in this way اللي شايفينه هون. add يعني حط one of the factors اللي هي 1 sigmoid من السكوير اللي تحت, and then plus 1 and minus 1 here in order to يعني هذه the effect of them is 0, ما بتعمل شيء. And now I can combine things in this way. بكتشف انه the gradient of a sigmoid is 1 minus sigmoid ضرب السيجمويد. And this is a realization. And now I can replace all this right here with one gate called the sigmoid gate. بيطلع لها downstream gradient واحد, local gradient which is this 1 minus sigmoid x ضرب sigmoid x, and an upstream gradient, and I can directly chain those within one gate. So خففت عدد الجيتس من 4 ل 1. good. اول optimization فهمناها. اوكي. more optimizations.
فواز عنده سؤال كان دفع ايده.
يس تفضل.
لا بالغلط
بالغلط يا خيي, بس خلص شو باك انت. The second optimization is some patterns that we need to focus on in backpropagation. Some patterns are the add gate, most probably شفناها. The local gradients in the add are 1. So an add gate will gonna distribute the gradient equally to its parameters. This is a very important realization, especially in papers or in architectures that introduce skip connections or residuals. Like the transformer architecture, it's full of residual connections. And those residual connections are meant to, I'm not going to talk about vanishing gradients and exploding gradients, but those residuals are meant to, if you want, make our architecture more powerful and make it escape some problems. And we use those residuals اللي هن خاصهم بالadd gate, since we know انه an add gate will gonna distribute the gradient equally to all parameters. Multiplication will gonna swap the inputs as the gradients, and then we can basically hard code this دغري يعني. The copy gate will gonna just add the gradients. So if a neuron is taking 2 inputs, قصدي 2 outputs, يعني it's connected على 2 neurons غيرها, we're gonna just add the effect. The max gate will gonna route the gradients, يعني حطفي واحد من branches, since the effect of the minimum is 0 on the cost لأنه ما أخذته أصلا. So the gradient of it is 0 and كل شيء وراه is 0 لأنه I'm chaining with 0. So these are important optimization. Yes.
يعني هيدي الماكس جيت هي كمان راليو, مش هي الاكتيفيشن هي ماكس جيت, ما هيك راليو اكتيفيشن.
Yes, max between 0 and the input.
اوكي. سو بالراليو بس يكون 0 يلي حيطلع لنا اياه هو حطف النيورون, ما هيك؟
Right, and everything وراها حيصير 0 لأنه I'm chaining with 0. every gradient وراها حيصير 0. طيب. This analogy of gates is very important in deep learning. Most deep learning frameworks frame their design in this ways, in the way of operators, in the way of blocks. So in PyTorch إذا فتحنا الريبو, we're gonna have large amounts of scripts in C and C++. Some are in Python, and these scripts are nothing but these blocks: a plus, a minus, an add layer, a copy layer, a batch norm, heck. So these are blocks that we build our neural networks with, and all are defined with local gradients, and the full optimizer will gonna link the upstream gradient with the downstream gradient using the local gradient. Okay, so far I've been talking about gradients flow, but with scalars. Thing is, in neural networks we deal with tensors, with matrices, sometimes with tensors. So the analogy of scalars is scalable to this high dimensional stuff, but it's not exactly the same. Like, let's think of things in this way. If x is a scalar and y is a scalar, and I'm trying to see the effect of x and y, it's just a one number. Let's agree it's a one scalar number. We're gonna say that the effect of x and y is this point. So dy over dx is a one scalar. But if x is a vector in n and y is a scalar, and I need to see the effect of x on y. I need to calculate dy by dx يعني. I'm gonna have an effect for every number in x on y, and this is also a vector, right? Because every number in x have its own effect, so this is a vector, and it's exactly the same size or the same dimension of x. So our gradients will get our dy by dx will gonna be a vector in n. Now let's take the extreme case in which it's we're dealing with two vectors, x and y, and we need to figure out the effect of x on y. We need dy by dx. Who will gonna guess what's the dimension of the gradients and of the gradient data structure and y?
فيك تعيد السؤال؟
لا ما عم بتركز انت.
مركز بس ما سمعت منيح.
Now let's deal with the extreme case. انه I'm dealing with two vectors x and y, and I need to figure out the effect of x on y. So I need dy by dx, and both are vectors. Who will gonna guess? يعني guess the dimension of the gradient data structure. Data structure بتحط بقلبها gradients. Guess its dimension. We said that in the case of vector scalar, I need an element for every element in the vector, so it's in the same dimension. What if both are vectors? شو حتكون
مش
dimension تبع data structure؟
we multiply both dimensions مش هيك؟
يا برافو عليك، يعني it's a
لأن
matrix,
كل
right?
واحد لأن فينا نعتبر كل element بتاني فيكتور عم يعمل الجريدينت، إنه
صح،
عم بيطلع الفيكتور of gradients.
Right, يعني every element in x will gonna have its effect on y. So assuming both are n, it's n squared, right? أو nm, it's n times m. And whenever I store gradients inside a matrix, I call this matrix the Jacobian matrix. هاي سقطت لي 201. Let's take a close look now at a more real example where we backpropagate with vectors. Say that the loss is a scalar, loss is still one number, and I have a vector z with the dimension dz. I get an upstream gradient, يعني جايني gradient من z, which is a vector, right, in the dimension dz. Now I need to calculate the effect of x on the loss. So I need to calculate the effect of x on the z, and the effect of y on loss. So the effect of y on z. We said that x is a vector, y is a vector. So so every element on x will gonna have its effect on z, and both are vectors. So I'm gonna store this in a matrix, dx by dz. Same thing for y. It will gonna be dy by dz. Yani every row is an element in y, and this element in y is the columns are saying this element in this row is affecting this element in z by this entry. يعني ما بعرف اذا خلصت عليكم هلا، بس انه basically it's a matrix where every element is affecting on every element. In the same sense, we have the upstream gradient getting from the layers in front of me. The downstream gradient is me, and the effect of x on z. This matrix is called the local gradients. Okay, let's take a close look at the backpropagation with vectors, and this is the ReLU activation, which is the max between 0 and x. Let's say we have a four-dimensional vector. Vector of size 4 getting inside a ReLU. The output is the positive numbers will gonna keep themselves as the same, and the negative ones are gonna be zeros. So for 1 it's 1, for -2 it's 0, for 3 it's 3, for -1 it's 0. Now I need to backpropagate, and I need something called the upstream gradient. Let's assume the upstream gradient is given to us, and it's by nature من الlayers اللي قدامي. And just throwing numbers right here, the upstream gradient is 4, -1, 5, and 9. Now let's calculate the dy by dx, which is the local gradient. What's the effect of x on every the effect of x on every element in y? observation انه this is pointwise, so this x right here will gonna just affect its output. It will not gonna affect this and this and this and this. صح؟ متفقين عليها هاي؟
متفقين.
So if I passed, so if I need the effect of this one on itself, it will gonna be 1, and then 0 for every other element. Same for -2, but -2 is flowing to 0. Flowing to 0, we're gonna have no effect on the cost function. So d0 by -2, 0, and 0 for every other element. So I'm gonna have a row of zeros. This element is not affecting at all the cost function. على ال 3 مثل اول example 1. على ال -1 it's 0 مثل تاني element. And this is the Jacobian matrix, which is the local gradients dy by dx.
So
chain them.
sparse.
Yes, chain them with the upstream gradient. Have a matrix multiplication. Basically, we're gonna take each row multiplied by the full column. The full column. Take the first row and multiply it. We're gonna have the first element. Take second row and multiply it. We're gonna have all zeros. Take third row and multiply it. You're gonna have the third row, اللي هو 5. Take the last row and multiply it. You're gonna have all zeros. So بيطلع لنا 4 0 5 0. Very important thing to notice in this matrix is so sparse, right? صح ولا لا؟
يعني كتير فيها
So-
زيروز اللي ما بيعرفش يعمل
Right.
سبوتس.
Yes. So a good engineering optimization to do is to make our hardware very adaptable to these matrices, to store them in a very efficient way and make computations through them in a very efficient way, different than a matrix that it's not sparse.
Why not
Or we can,
software
yes.
مثلا في ماتريكس ريبريزنتيشن لسبارس عفوا في ريبريزنتيشنز لسبارس ماتريسيز بنبطل نستعمل هيك
Right.
ماتريكس.
Right. Or what we can do is, in the software perspective, something smarter than making a special representation for the matrices, is that to hard code the ReLU gradients. We know that the ReLU, if it's negative, the gradient is 0. If it's a positive, the gradient is 1, and it's not affecting anything but itself. So we can directly put the gradients as 1 0 1 0 and multiply them with the upstream gradient and get the input. So I'm gonna say that a simple if condition, a ReLU we're gonna have, يعني if it's bigger than 0, it's 1. If it's smaller than or equal to 0, it's 0, and just chain this with the upstream gradient. And this is a very efficient trick in which in PyTorch the ReLU activation is simply 2 APIs. The first is forward, the second is backward. Within this API, we have a one if condition, one if else. For the forward, if أكبر من 0, I'm gonna return x, else 0. And in the backward, if أكبر من 0, I'm gonna return 1, else 0. Simply يعني. Let's backprop with matrices and see the tensors in action. This is a very هلا يعني خلص صارت هلا basic مثل اللي قبلها. Say you have z, it's a dz by mz dimension, and you are getting an upstream gradient which is a matrix. Since z is affecting a scalar, which is the loss, so it's in the same dimension, dz by mz. Every element in dz mz have its effect on this loss. I need to backpropagate this into x and y. So the effect of x is مين بيحصل الديمنشن؟ لأنه it's also a matrix affecting matrix. So
نيو ماتريكس يعني هي بهيدي الحالة.
yes.
دي اوكي. اصلا لا في مشكل
اللي شو المشكل؟
انه هون عم نعمل ماتريكس multiplication.
يس لا سوري هول الديمنشنز.
دقيقة، ما هي هي 2 dimensional صح ولا لا؟
X is 2-dimensional و Z is 2-dimensional also, so every element in X is affecting every element in Z. يعني every element in X will gonna have a matrix in which it's equal to the dimension of Z. يعني every element in X عنده
يعني 3
corresponding
dimensional.
matrix. كيف 3؟ ما أنا عندي n square elements بX و n square elements بZ.
كيف n square مش d by m و d by m؟
صح, which is a matrix. وعندك dz by mz which is also a matrix. عم بحكي عن quantifying the number of elements. Take each element in z in x and each element in x بده يكون عنده matrix كامله اللي هي الz كيف عم بيأثر عليها. Every element هناك مع every element هون n square times n square, or اذا بدك كل الديمنشنز مضروبين ببعض. So it's a tensor.
Okay,
It's a 4D tensor. Right? It's a 4D tensor for every element affecting for every element. And I can backpropagate كل هول gradients. Now I'm gonna
بأي حالة بيصير في هيك 4D tensors مثلا؟
in the hidden layers مثلا. Your
يعني
input.
هيك بنجمعهم مع بعض كلهم هيك قصدك؟
Yes,
انه
نجمع مع بعض.
مثلا after computing the gradients of the parameters of the third layer, okay.
Yes.
I need them للprevious layers، فمش هيك بدي احافظ عليهم فبحافظ عليهم بتنسرز. اوكي.
100% clear. Yeah. Now by now you should have a clear vision or a clear view عن backpropagation, and I'm gonna wrap things around. Recall what Basil said امبارح, why activations. Say you have this input space and you need to make a linear classifier in which a linear boundary classifying those two regions, those two input regions. There's no, by any sense, a linear line that classifies those. So we have one of two approaches to overcome this problem. The first is feature transformation. Yeah, we get a domain expert to make us more features or transform our features in order to make them linearly separable, or we make some mathematical tricks, like instead of representing them in the xy domain, we represent them in the r theta domain, and then they are linearly separable. Or we use nonlinearities, and with nonlinearities, with high dimensional data مع nonlinearities كل شيء, we need big capacity models which are neural networks that are powered by nonlinearities. So here we come, neural networks, big computational differentiable computers with nonlinearities. صار في عندنا neural networks. A very popular choice for nonlinearities within the hidden layers is ReLU. As I said, it's 2 APIs. Each API is one if condition, so it's very efficient to use. Plus, it will gonna help us in the vanishing gradients problem. ما هحكي عنها اليوم كثير, بس you can imagine that it overcomes some problems within the 10H and sigmoid when it comes to gradients, since a gradient of 1 is always better than a gradient of 0 point something. خلاص, think of it انه it will gonna give us smooth gradients. A problem with the ReLUs انه we have this region that is zeros. يعني اذا كانت النيورون outputting negative, it will gonna be a dead neuron لانه zeros, لانه I'm gonna subtract it with a gradient which is 0, it will not gonna update بكل training loop. We have some ways in research around it. They use leaky ReLUs in which we have slight deviation than 0 من الزيرو region. امبارح في واحد بالسيشن قال GLU, ما كنت بعرف شو هي. I looked it up قبل السيشن today. It's very similar to leaky ReLUs while we sample gradients within structured to a normal distribution تحت الزيروز. Anyway, it's also to overcome the problem of dead neurons.
Why not 10H?
مرة تانية بس basically look at the 10H. If the weights are big, the outputs are big, you're gonna hit those tails.
طب why 10H؟ ليه؟ اوكي واضح ليه ما لازم استعملها، انه مش ما لازم، انه ليه يفضل، لا ليه انه بستعملها، انه لشو استعملها اصلا؟ امتى في حالة منيح استعمل فيها 10H؟
مش على راسي بس what I know انه every paper قبل 2014 قبل 2012 كانت تستعمل 10H in the hidden layer.
اوكي
بس مش على راسي هلا يعني وين بستعمل 10H. اوكي
هلا بتذكر
maybe let me make a claim. Maybe if you are guaranteed that يعني if you guarantee in your activations are small enough يعني between -5 and 5 and you hit this region اللي هو kind of linear, maybe it's a good choice to put it in H if you guarantee stuff.
اوكي
بس صراحة ما عندي جواب واضح. طيب to recap, neural networks have nothing to do with biological neurons. Maybe we take the analogy of nonlinearities in which neurons that fire, but there are certain blocks, computational units. We use gradients to nudge them. We use learning rates to quantify this nudge, but they have nothing to do with biological neurons. They are computational units, but at the same time they are differentiable, which make them very powerful. Take this lecture and move it forward. Every architecture, every deep learning architecture, we're gonna have backpropagation within its hiddens, and backpropagation is very. We have many engineering tricks غير اللي حكيت عنهم اليوم. All optimizations اللي حكيت عنهم. We have many engineering tricks to make it better. Take it forward. Every paper بتقروها try to not also understand the input, output, and loss, but understand also how gradients flow. Since when you understand how gradients flow, you're gonna have the big picture. Even in the certain advancements in AI, you hear about RLHF, reinforcement learning from human feedback. Yes, reinforcement learning is getting back, but supervised learning is also being better at each time, like DPO. DPO is a method which is the new RLHF, and we have gone back into supervised learning. Not saying RL is bad. Some people say that RL is the absolute intelligence, but supervised learning will not gonna be away for any reason. So backpropagation is very important for every differentiable computer بدنا اياه هلا. That's it. وإذا حدا عنده أسئلة يسألني هون. That's it for me.
يعطيكم العافية.